Talk. All right, our next speaker is Guang Yao Zhou from Vicarious. Guang Yao, if you're here, you can turn on your video. So I see that Guang Yao is, there we go. Hi, Guang Yao.
Hi, can you hear me?
Go ahead.
Can you hear me okay? Oh, okay.
Hear you, great.
Okay, great. So I'll share my screen and hi everyone. So my name is Guang Yao, and today I'm going to talk about mixed Hamiltonian Monte Carlo for mixed discrete and continuous variables. First, to give you some background, I think a lot of people here are familiar with Hamiltonian Monte Carlo. So Hamiltonian Monte Carlo, or HMC for short, is a powerful MCMC method that samples from continuous target distributions by introducing auxiliary momentum variables and simulating the so-called Hamiltonian dynamics. So HMC has enjoyed remarkable empirical successes and is adopted by a lot of popular probabilistic programming systems. But as a few speakers that has mentioned today and the day before, HMC has a fundamental limitation, which is it can only be applied to distributions with continuous variables, but it cannot be applied to distributions with mixed discrete and continuous variables. So in our work, our goal is to enable HMC to efficiently sample from a target distribution with both mixed and discrete and continuous variables, which are very important in many applications. So there are some existing approaches for handling this particular task, including, for example, to explicitly integrate out the discrete variables, which is adopted by, for example, Stan and Pyro and non-Pyro. But the problem, I would say, is only applicable on a small scale. It would run into scaling issues if you have a lot of discrete variables with a lot of states. And in some cases, it can't be always carried out automatically. So another alternative is to alternate between continuous HMC updates and generic discrete updates. So this is adopted in packages in, for example, the PYMC3 or Turing GL. And there are two problems. I would go into more details in later slides, but I would briefly mention here, which is the discrete updates can only be done infrequently because you have to alternate between the two different kinds of dates. And it's also harder to make long-range proposals in this kind of approaches. So the third approach, which I would say is the most promising one, updates discrete and continuous variables in tandem. Some existing approaches include public path HMC and the so-called discontinuous HMC, or DHMC for short. So one issue with these approaches is, for example, PPHMC only works for phylogenetic trees, and the DHMC is best suited for ordinal parameters. So in other words, they are not generally applicable to any distributions with mixed support. And DHMC also has inefficient embedding and algorithmic structure, which I would go into more details in later slides. So in our work, we propose the so-called mixed Hamiltonian Monte Carlo, or MHC for short, which is a novel family of MCMC methods that involves the discrete and continuous variables in tandem. It's applicable to any distributions with mixed support, and it can be easily incorporated into existing HMC implementations. So to give you a sense of how MHMC works, I'm going to start with a simple illustrative example on a 1D Gaussian mixture model. So you can see on this figure that this is the kind of model that I'm considering, which is one-dimensional and has 4 mixture components. So to go back to my previous slides, I mentioned that the most promising approach is to update discrete and continuous variables in tandem, and that's exactly what MHMC is doing. But if you think for a moment, and if you try to do it naively, then the naive approach to handle that is to make Metropolis Hastings updates within an HMC iteration. And in this concrete example, we would look something like this, where you propose a discrete state given where you are now, and you use acceptance rejection step to decide whether you are going to accept the discrete proposal or not. But as we can see in this figure, that kind of proposal, that kind of updates leads to biased examples. And in the MHC framework, specifically when we apply the MHC framework to this particular example, we will see that the framework implies a very simple change on top of the naive Metropolis Hastings within HMC updates, which is instead of calculating a probability and make an acceptance rejection decision, it's going to explicitly record the so-called auxiliary variable, which encodes the auxiliary kinetic energy. And it's going to look at the kinetic energy and compare it with the energy difference to decide whether you are going to accept or reject. And if you accept, you are going to modify the kinetic energy accordingly. So one intuition and as you can see here, it corrects a bias in naively making Metropolis Hastings updates within HMC. So an intuition for why that will work instead of this kind of naive MH updates within HMC is to note that in the final Metropolis Hastings correction in HMC, we are also going to look at this auxiliary kinetic energy. So in some sense, instead of making decisions at every discrete updates, we instead are going to accumulate those decisions in the form of this auxiliary kinetic energy and then make the final decision in the end. So that somehow corrects some inherent bias that gets introduced in these kind of approaches and gives us unbiased examples. And furthermore, if you look at, so this is a visualization of the proposed MHMC kernel on this simple example. So if you look at this example, you will see that the blue curve shows you the evolution of the discrete random variables, and the orange curve shows you the evolution of the continuous random variables. And by evolving discrete and continuous variables in tandem, we are able to make long-range proposals. And in this particular example, it traverses all four mixture components for this example in one HMC iteration. So more generally, this is the full MHMC algorithm, which is applicable to arbitrary distributions with mixed discrete and continuous support. So this might seem a bit complicated when you first look at it, but here's the important case. Here's the important part. Basically, the essential idea is, as we're showing in the simple 1D Gaussian mixture model example, we're going to alternate between continuous and discrete updates. And in discrete updates, we're going to rely on a specific proposal distribution to make a proposal and try to move to a different state. And whether we can move to that different state is determined by the energy difference, which is calculated this way, which is slightly different, and also takes into account the continuous variable. And we also have the auxiliary kinetic energy, which we can use to decide whether to accept or reject. Big advantage of the MHMC algorithm is, as you can see, it's very easy to incorporate this kind of mechanism into existing HMC implementations because it's literally just alternating between existing HMC updates and the discrete updates. But the difference is now we are doing both in tandem, and we can also update the discrete variables within a particular HMC iteration. So now I'm going to come back and talk about comparison of MHMC versus some alternatives. One alternative is to alternate between HMC updates and discrete updates. So here is the visualization I already showed you. And as I mentioned, MHMC can make really long-range global proposals within one iteration, which, because of the use of HMC-like mechanism, can be accepted with high probability. But in this, for example, in this particular example, what would happen if we really start alternating between HMC updates and discrete updates? Then at each for each HMC updates, because we are fixing the discrete random variable, then we most likely would be able to only move within one mixture component. We won't be able to. It's very unlikely for us to move to different mixture components in the continuous updates. And also, for the discrete updates, since we're fixing the continuous random variable, chances are we most likely would only move to a discrete component that is the neighbor of our current component. And if, for example, we happens to end up in the middle of a mixture model, in the middle of a mixture component, and then we try to make a discrete update, then even moving to a neighboring discrete update is difficult. But in contrast, in MHMC, because we are essentially constantly trying to move to different discrete updates within an HMC iteration, we get plenty of opportunities to move to a different mixture component. And when we get near the boundary, we make an attempt, and as you can see, we frequently succeed. If we succeed, we move to a different mixture component, then the continuous part can continue to traverse the new mixture component. So we repeat this process, we get really long-range proposals. And as I mentioned, because of the use of HMC-like mechanism, those long-range proposals can be accepted with a high probability, which makes the method much more efficient. But then we come back to the question of what's wrong with some of the existing approaches, which also updates discrete and continuous variables in tandem. So there are two approaches that I can find in the literature, and as I mentioned, the probabilistic path HMC method only applies to phylogenetic trees, so that's not really very generally applicable. And another competitor is the so-called discontinuous HMC or DHMC, which in theory is also generally applicable. But the problem with that is it relies on an embedding that works best for ordinal parameters, and in particular relies on this kind of embedding. So if we have a discrete random variable, then DHMC assumes it takes integer values and it embeds that into a one-dimensional continuous state space. So the problem with that is, so here is a simple example. So the problem with that is then it's really sensitive to the ordering of the parameter. So here is the same 1D Gaussian mixture model example. This is a canonical representation of the means where I order the four components as -2, 0, 2, 4. As you can see, that's a canonical ordering. In this case, DHMC works, although you can see that I need 5 times 10 to the 6 samples to perform well, while for MHMC it's more efficient and it does it with 10 to the 6 examples. But where I exchange the order of the two components in the middle to -2, 2, 0, and 4, then DHMC fails. And it's also intuitive why it fails, because it relies on this kind of embedding. So if we make this kind of change, some neighbors that should be neighbors in the canonical embedding and are no longer neighbors. So when you try to move to a neighbor, it's actually very hard to move to your neighbors in this kind of examples, and that makes it break down in this kind of cases. I will also show an example in a later numerical experiment. Basically, it's hard for DHMC to be applied to distributions with complicated discrete state spaces. But why can MHMC do it? Because the difference is in MHMC, I actually explicitly keep the discrete random variables. So I have the discrete random variables, and I have some continuous embedding, which is very simple and just for the discrete and continuous part. So when I try to move across the discrete state spaces, I still rely on explicit discrete proposal distributions, which gives me maximum flexibility in terms of how I can move around. And I don't need to worry about any kind of topology when I make the embedding of the discrete parameters into the continuous state spaces. So basically everything is everything's neighbor, and as long as you can move it using the proposal distribution, you're good. So that's why MHMC can be easily applicable to any distributions with mixed support. And furthermore, in DHMC, it has this special algorithmic structure where you have to update all discrete variables at every step, at every time. And that is inefficient in some cases. But in contrast, for MHMC, I can actually flexibly control how frequent I want to update my discrete variables and how many discrete variables I want to update at each time. So I would briefly go through some numerical experiments. Basically, I compared MHMC with a lot of other alternatives like DHMC, or alternating between HMC updates and the discrete updates. For example, the HMC within Gibbs, the no U-turn sampler, the not sampler within Gibbs, and specialized Gibbs sampler. So this no U-turn sampler operates on the or the marginal distribution. It's integrating out the discrete random variable, and I'm just using it for one particular example, which is a GMM, which is a Gaussian mixture model.
Guangyao, sorry to interrupt. You have just under 5 minutes left.
Okay. So in terms of performance measure, I'm calculating the minimum relative effective sample size, which is basically the effective sample size, minimum effective sample size across all dimensions, normalized by the number of samples and estimated using multiple independent trends. So here is a slightly more complicated Gaussian mixture model, which is 24-dimensional. So I'll briefly summarize the results, which is all the samplers are tested accurate, and it's more efficient than some of the alternatives. But the surprising thing is, in this example, MHMC is even as efficient as NUTS, which explicitly integrates out the discrete random variables and operates all the marginal distribution. So that is actually a bit surprising, and yeah. So another example is variable selection for Bayesian logistic regression. Again, some brief summary of the results, which is all samplers are accurate, and MHMC outperforms some of the alternatives that I look at. And in addition, I look at how MHMC the performance of MHMC changes with some of the parameters, and it turns out similar to vanilla HMC, it also exhibits some kind of U-turn behavior where if the travel time is too large, it starts to double back and gets worse performance. And in addition, it also actually benefits from distributed and more frequent discrete updates. So given the same number of discrete updates within an HMC iteration, if you actually spread those out, it gives you more efficient sampling. But the downside of that is then you have to do a lot of discrete updates. That means you also have to do a lot of continuous updates because we are alternating between the two, and that might lead to a lot of potentially expensive gradients evaluations. But empirically, we do observe that that kind of updates are more efficient. So here is a final example, which we tested on correlated talking models. So in this case, actually, the DHMC case fails because in this example, the discrete state spaces are very complicated. And we also tested specialized Gibbs sampler, and it turns out the specialized Gibbs sampler also occasionally fail. To understand why it fails, we look at a particular example in which the Gibbs sampler gives a different mean than some alternatives like HMC within Gibbs and MHMC. As you can see, the reason that Gibbs fails is it gets stuck in a smaller range of the state space, and it's not able to fully explore the state space. So that gives it something tree explore that's like this. While for HMC within Gibbs and MHMC, which gives the same sample posterior sample means, they explore the state space much more efficiently. And also, as you can see, MHFC mixes much faster than HMC within Gibbs, and also than the Gibbs sampler. So some conclusions are MHFC evolves discrete and continuous variables in tandem and is easily applicable to any kind of distributions with mixed support. It can be easily implemented, and it's more efficient. So yeah, this work is recently accepted to YIPS 2020. So there's a preprint available, and there's also code available. So I can take some questions if there are any.
All right, let's all thank Guangyao in chat for a great talk. I think we have time for one, maybe two questions. The first question is from Nima Aurora, and he says, how do we tune the amount of kinetic energy that is injected for discrete variables, similar to the tuning of the mass matrix for continuous variables? And by the way, he says this is a very cool idea.
Okay. Yeah, so I guess the question is for the discrete random variables, it's actually slightly simpler in the sense that the kinetic energy only plays the role of like I showed in the 1D Gaussian mixture model example, it only plays the role of replacing the Metropolis Hastings updates step, and it records how much it plays a role of some kind of momentum, and it keeps you going, and it gives you some it records some history. So in that sense, there's no mass matrix. So in the actual implementation, we will say that we always sample the kinetic energies at every momentum resampling step. We sample the kinetic energies from an exponential distribution, and then we just start working with that. So that sampling of from the exponential distribution is similar to Metropolis Hastings updates. So yeah.
Thank you. Sure. Okay, and then maybe one quick question from Hongay. He says, thank you for the interesting talk. Would it also be possible to use MHMC with non-discrete generic proposals within HMC, for example, slice sampling?
Yeah, that's something that I haven't considered. So basically right now, the framework ties closely into HMC. Even for the discrete part, I'm actually emulating HMC by introducing the momentum in the form of the kinetic energies. And when I evolve the system and do the updates, it's closely emulating the continuous part. So if you look at the full paper, the actual theory builds on something that's slightly more complicated, which has explicit location and momentum variables, even for the discrete part. And then you also evolve the Hamiltonian Carlo for that. So in that sense, it's not possible to incorporate that. But that's something that I've been thinking about. Basically, some generic framework to flexibly combine discrete and continuous updates so that they can evolve in tandem. But that's still ongoing.
Great.